Welcome to this lecture. This one is about the limitation and extensions of PINNs. Last week, we discussed the applications of PINNs and how they can be used for loads of different problems, from like simulation to inversion to equation discovery. And I really bigged up PINNs. I said they're a really impressive new technique. And what I think this lecture is about is kind of bringing it down to earth and showing you there are limitations of PINNs. And try and give you an idea of the different ways that you can use them and where they're useful. There are also many extensions of PINNs, and I've only been showing you the very basic kind of vanilla PINN at the moment. And so I'm going to try and cover a lot of different ideas that try to make them more powerful and also overcome these limitations as well. So before we get into that, let's just quickly go over the timeline again. So, yep. We're on this third lecture of physics-informed neural networks. So there's a couple of things to note. We have 2 holidays. There's actually 2 weeks off. So we're not having lectures for the next 2 weeks. And then when we come back, we'll be covering a new topic, which are neural operators. And Sid, the other lecturer, will be taking over for that whole section. And I'll be coming back for this differentiable physics 2 lectures on that. The other thing is, I think we sent you some more information about the project. So if you have any questions on that, I can answer that at the end of the lecture as well. But we should be giving you more information at the tutorials as well. So feel free to ask us questions. Okay, so before we get into the lecture, let's recap what we did last lecture. So let's just quickly remember what a physics-informed neural network is. I'm sure you all know this now. We've had a few lectures on it. But this is the simplest use of a PINN is to solve differential equations. And so, for example, we have the Burger's equation here. And then it's a very simple idea. We just say that the neural network, as a function of the coordinates here, is a direct functional approximation of the solution to the PDE. And then we train the PINN with this loss function, which has 2 components. The first loss we call the boundary loss, which asserts along the boundaries of the domain what the values of the solution should be. So for example, with this problem, it's just time equals 0, u should be minus sine x, for example. And then we have the physics loss, which is the interesting bit, which makes sure that at many points, we call them collocation points in the domain, the underlying PDE, the residual of the underlying PDE is satisfied, so that the PDE is honored every point in the domain. And if you train it, you can start to train PINNs to solve many different differential equations. So what's exciting about the Burger's equation is we have this shock, and the PINN is able to kind of model that quite well. Okay. And then we actually, I did some coding for you last lecture, and we went more into the details of how you actually train PINNs. And one of the kind of interesting things is how we actually get these derivatives in the physics loss. So how do we get the derivative of the network with respect to its inputs rather than its weights, which is what we normally do when we use gradient descent to train networks. And so I tried to convince you that we can use autograd or auto differentiation, and it's really powerful, and it lets us compute arbitrary derivatives in our computational graph, and then also create a new graph from those and treat those as a new thing that we can differentiate through again. So we use this create graph functionality in PyTorch to get our derivatives with respect to our inputs. And then we differentiate through that again to get our derivatives with respect to our weights of our neural networks when we're training the network itself. So this is a really powerful feature of autograd and is why PINNs can be trained in such an easy way in just a few lines of code in PyTorch. Okay, and then the other thing that I showed you was we just talked about PINNs for forward simulation with that Burger's equation example. But I showed you that we can also extend PINNs to solve inverse problems. And so this is the problem where you have some observational data and you want to find the underlying parameters of the PDE, say the initial conditions or some constants in the PDE. And all you have to do when you're training the PINN is add those extra parameters as additional learnable parameters inside your loss function. And then the PINN starts to, when you're training the PINN, it not only learns to simulate the observational data, but it also learns these underlying parameters. And so jointly does an inverse and a forward problem at the same time. And of course, to be able to do this, you have to add an extra term, which is this data loss. And so this is the observational data that we have, and it could be noisy too. And then we took it one step further, and we said pins can also be used to actually try and discover something about the underlying differential equation itself. And so then you don't actually know D, which is this differentiable operator. So this represents any sort of PDE. And so we say we have this dictionary of differentiable operators. This is just a collection of like d by dx, d by dx squared, etc. And a sparse matrix of coefficients, big lambda here. And we try and learn that matrix, which if we take the coefficients out, that actually tells us what the PDE is. So yeah, the pins are very flexible and can be used across all these different types of problems. Okay, cool. So I said that this lecture is all about trying to understand the limitations and extensions of pins. And so I think there are three fairly large or major limitations. These are the computational cost of pins, the difficulty of converging pins for some particular PDEs, and also the challenge of scaling them to more complex solutions. So when the PDE has like multi-scale features or discontinuities and such. And so we'll try and talk about all of those and also the extensions that are happening in the field to try and overcome these limitations. And then we'll just end up with a discussion on when should we actually use pins, when's actually a good idea to use them. Okay, so yeah, so I think I've already convinced you over the last lecture what the advantages of pins are. And so I'm going to go through them very briefly. The big one, or the biggest ones are that pins are mesh free. So this is a massive advantage compared to finite element methods, for example, where you have to spend a lot of time creating like a high quality mesh for the simulator. So remember, pins give us an actual function, which we can query at any point in space rather than a discretized solution. So it's kind of a very different way of thinking about the solution. Where I think pins are most powerful is when they're extended to solve these inverse problems or kind of equation discovery type problems. Particularly when you have some kind of, we call them messy or mixed problems. It's where you have perhaps a little bit of data, but not very much, like a few observational points. And perhaps you know something about the physics, but you're not entirely sure what the underlying coefficients of the PDE are, for example. This is typically a situation where traditional algorithms would require many forward evaluations. So you would have to run your finite difference simulation many times, which is expensive. Typically, this is where pins will perform the best. And we'll get onto why that is later. Yeah, they also have kind of analytical gradients, which is useful if you want to do, once you've learned your solution, if you want to do some sort of sensitivity analysis on it, for example. And then pins compared to like naive data-driven machine learning is basically unsupervised. You only need information about the solution at the boundaries. And so this is really cool as well, compared to these kind of data-driven methods. Right, so we're going to get onto the limitations. So computational costs. So can anyone tell me why are pins, especially if you're just doing forward simulation, why are they expensive? Anyone know? Yeah. Yeah, exactly. That's one very good reason. So as I said last lecture, when you're training the pin, most of the cost of training it is not actually computing the solution of the pin, the forward pass of the network, but it's actually using autograd to get the gradients and then differentiating through those again. So yeah, for sure. So in general, if you think about the comparison of physics-informed neural networks to kind of finite difference simulations, physics-informed neural networks rely solely on optimization. So we have to optimize the solution. Whereas finite difference simulation, it's kind of just an algorithm that we just run forwards. And so that optimization in general, as you're saying, is the most expensive bit. So for example, I showed this example of pins solving the wave equation. So we start with an initial condition here of just a wave in the middle or a point source in the middle. And then we try to teach the pin to predict the solution at later times. And yeah, this particular example it uses a fully connected network with like 10 layers, 1,024 hidden units, has a randomly samples collocation points, 500 samples every iteration of gradient descent. So in terms of machine learning, general machine learning, this is like a very small network with you know, hundreds of thousands, maybe 1 million parameters. I would have to work it out. And it takes about an hour to train. So this is just solving the equation. But if I ran finite difference simulation on this, and I did to create this ground truth, it takes, you know, a minute or so. And this is because the network is like, we're relying on optimization to train. And also we're using a GPU here, so it's not like it's just training on a single CPU. And this is typical of when you're using PINNs to solve like more complex PDEs that are not just really, really simple toy problems. And the killer here is that we have to, once we've trained the PINN, and we want to run a different simulation, say we want to shift the source location over here somewhere, we're going to have to retrain the PINN every time. And so this is the killer, is they have to be retrained for the different initial conditions. And so in this kind of raw form, it's just not competitive to, you know, this ground truth finite difference simulation. Okay, so that's limitation 1. Limitation 2 is convergence. So what do I mean by this? So I touched on this very briefly last lecture, and this is the kind of the issue of the competition of the different loss terms in the PINNs loss function. So remember, we have this boundary loss here, which is, again, it's asserting the solution at the boundaries. And then we have this physics loss, which is trying to make sure that the solution obeys the differential equation. But to balance them, we have to have this like lambda value here, or multiple lambdas for each kind of term in the loss function. And this is just a hyperparameter. This is like, it's actually quite difficult to choose in a principled way what lambda should be. Another thing you need to think about is the kind of units of each of these terms. So for example, the units of this term is just the units of whatever the solution is. But the units of this term is like in units of its derivatives. So they're not necessarily going to be the same magnitude. So you can't just choose lambda equals 1, for example. And maybe you want to weight some of the boundary conditions like larger than others. It may make sense to do that. So yeah, what happens if lambda is too small? If lambda here, if it's too small, then we rely very heavily on the physics loss. So why wouldn't that work? If we just train on the physics loss, who knows the reason?
You could learn any solution from
exactly, yeah. So the solution we learn might not be the unique one, it might just be a random particular solution. And in general, it could be a very simple solution, because the PINNs like to, in my experience, they converge on kind of very simple solutions. So for example, the Burger's equation, I think if u equals 0 everywhere, we just solve it as a particular solution, which is obviously not helpful for this problem. Okay, and then if lambda is too large, then we're basically just ignoring the physics loss. And then we're just training a network which just fits at the boundaries, but has something nonsensical in the middle of the domain. So you can see how there can be some competition here. The PDE loss might want to learn like an easy one, and then the boundary loss is trying to make it learn a harder solution, for example. And you definitely see this if you train PINNs, especially with more complex solutions. And so this is another example of the wave equation. I've made the problem kind of harder here because we have a very small point source. So this is our kind of boundary or initial condition, is that the wave field should start as this very small Gaussian blob. And then we're just going to let it propagate outwards. So the PINN's going to try and solve the solution through time. And we have a kind of complex velocity model here that it's going to go through. So this is just like a bunch of different Gaussian perturbations of the velocity. And what that does is it just kind of squeezes and pulls and distorts the wave field as it goes outwards. So you can see the solution here. And so if you train the PINN, just a standard PINN to try and solve this problem, what you see, so what's really interesting is if you look at this, the convergence curve of the PINN. So this is the test loss. This is like the difference between the PINN solution and ground truth finite difference simulation. And what you see is you would hope that this just converges nice and linearly or kind of smoothly. What happens is the loss is just really, really high for basically half of the training time. And you can see it actually gets worse. It really goes up higher and starts to thrash around a lot. So I call this kind of behavior kind of thrashing. And so what you can do is at the bottom row here, we're plotting the PINN solution at training step 20,000. So at this point here, where you would have hoped it would have started to learn something about the solution. But you see, all it's done is learn the boundary condition, and then at later times, it's just u equals 0. And so what I think is happening here is what I just described, is the physics loss is just preferring this simple particular solution, which is u equals 0 everywhere. And the boundary loss fits the boundary, and then there's a little bit of mismatch at some time point here. But it doesn't matter, because on average, the loss function is minimized. The physics loss function is minimized well. And then eventually, this seems to be quite an unstable kind of training problem or optimization problem. It does eventually figure out snap to the right solution, and it gets to it eventually. But you can see if I made this problem like slightly harder, added more time points, it is potentially very likely that the PINN wouldn't converge at all, and it would just end up thrashing around. And so this is not like the nice convergence laws that we have for like finite elements, finite differences, where we can say very precisely, if we have this many mesh points, we'll get this accuracy of the solution. So yeah, this is a big limitation. Okay, and then yeah, the final one is kind of coupled to the convergence, poor convergence of PINNs, and this is their ability to scale to more and more complex problems. So what do I mean by that? So I think if you've been following along carefully, every single kind of example that I've been showing you of PINNs has been of what I would call like a toy problem. You know, where you have like a classic one in Navier-Stokes is like to model the flow past a cylinder. And this is actually, it can get very complex if you go to like very turbulent flows. But the toy version is like a very well-known problem to solve. And the same with these wave equation problems. I've just been showing like a point source through like a simple layered velocity model. But what we actually care about in today's world, and it's very important when you're doing research, is to really think about this, is to say, all right, how do I go from this like toy problem to a problem that I actually really care about and want to solve and would have a big impact in the world today? So for example, like instead of the flow past the cylinder, we actually want to know the flow of the whole atmosphere, or the whole, you know, the climate itself. This is obviously a really important problem to be able to solve. And the same with the wave equation. We want to go from simple velocity models to predicting the impacts of earthquakes like across the whole of California, for example. And we know, if you look at traditional methods, traditional algorithms, we've spent decades, hundreds of years trying to improve these algorithms so that they can bridge this gap, so they can start solving these really complex problems. And so, you know, things that you have to think about when you go to this this regime is that you have lots of multi-scale kind of phenomena happening. So, you know, waves of different frequencies in the earthquake simulations, for example. You also have lots of different physics happening, so multi-physics simulations, and this is really challenging to put into traditional algorithms. Also, kind of coupled to this is like as the domain size increases, typically the frequency content of your solution increases, and this can really increase the computational cost of traditional methods. And then also, you really want to start doing these kind of more messy problems where you start incorporating real and noisy data. So for example, with climate simulations, we have many measurements of the Earth's climate. We really want to put that in to calibrate the model and make sure that the simulation is accurate going forwards. So in my opinion, there's a very big open research question is how do PINNs scale to these types of problems? And I think what's more interesting, I think it's given that it's going to be very challenging to scale PINNs. I think the more interesting question is in what ways do they scale differently to traditional methods? And I think that's the kind of interesting question. So let's think about a very simple scaling experiment to try and get like a first idea of how PINNs scale. And so what we're going to do is we're just going to use the PINN for like forward simulation. And so we're just going to solve like one of the simplest PDEs you can think of, like du by dx is cos omega x. So actually an ordinary differential equation, just a 1D problem. And we're just going to say u at x equals 0 is 0. So the solution here is sine x. And yeah, we solved the PINN, and I'm going to solve it for different values of omega. So in particular, I'm going to choose omega, which is 1, so a low frequency solution. And then going to choose omega as 15, so a much higher solution, a higher frequency. And so what you see, if I train the PINN on the low frequency problem, and I use just like 2 layers, 16 billion units. So this is a very, very small neural network. It gets the solution very, very rapidly, converges very, very nicely. And you can see the convergence curve here. This is the test loss as a function of training step. And it's the red line here. So you see within maybe 2,000, 5,000 steps, we get to a very low kind of loss. So it works very well. And then the interesting thing is if I take the same PINN, so 2 layers, 16 hidden units, and I just increase omega to 15 and train it, you see that the neural network itself is, well, there's a couple of things that are going on. The first is that you see it's only able to model a couple of the cycles of the solution. So why do you think this is? Why can't it model all the rest of the cycles? Anyone got an idea? So as you're adding more cycles in, the solution is essentially getting more complex. And so what's happening here is the PINN is not expressive enough to model the solution with more cycles. Remember, the PINN is not like fitting a sine wave, it's fitting like this weird function, which is like composed of activation functions. So for example, when you have a ReLU activation function, you can think of the output as like a piecewise linear fit of the thing that you're trying to model. And so the number of linear segments that you have depends on the number of like parameters of the network. So you can think if I've only got like a 300 parameters here, I can maybe only piecewise fit like 4 or 5 of the cycles of the solution. And I'm going to need to add more parameters to be able to be expressive enough to model to mathematically be able to model it. So what do we need to do? We have to increase the number of parameters of the PINN. So we can do that. So we add more parameters. So let's go from like 2 layers to 4 layers with 64 hidden units. This has got way more parameters. And you can see, yeah, for sure, it starts to model more of the cycles. It's more expressive, can start to model it. And what I had to do is really increase it even further to like 5 layers, 128 hidden units to be able to model all these cycles. But there's big downsides of this. There's like, first, if you just compare the numbers of parameters, you've got like 300 parameters up here versus 66,000 parameters here. This is not like 50. You would hope that it would just be 15 times. If you've got like 15 more cycles in the solution, 15 times more parameters. But it doesn't appear to be the case with this type of architecture. Yeah.
This problem in this addition, and those the same problems.
That's a good question. Yeah, I haven't tried that. So the suggestion is to basically, instead of using a physics-informed neural network loss, just to train it in a data-driven sense. And I think that would be an interesting test. I would suspect you would see similar results, but it wouldn't be able to fit all the cycles. Yeah.
Another question is for the bigger P.
Yeah.
Have I ever figured out the domain not covered in this branch?
Have I?
Yeah, I mean the domain not covered in the figure that you shown is a PINN except.
I don't think I understand.
If you want to just shoot the domain from -6 to 6, right?
Yeah.
Yeah. What about the other domain? Is the PINN except?
Do you mean if I like extend the domain or?
And the thing is the value derived by PINN is the same as the exact solution because we only show the domain from -6 to 6, right? What about
the rest of the domain? Yeah, sure. Yeah, so this is what we were talking about last lecture. Is remember I was showing the damped harmonic oscillator and the PINN like fits it within the domain, but it's only going to fit the solution where you have collocation points, and you'll still have the same issues of like generalization further out. So this would be different though if I added something to the network which it was like a prior that said the solution should be wavy. But for example, if I just had like a network with sinusoidal activation functions, for example, then this might work much better because it just has to learn like the frequency of that function. And so this is really important. This idea of like the priors or the inductive bias of the network is a super important and like interesting question when you're using PINNs or in general neural networks to model physical processes. So a fully connected network here, what this is really telling us is fully connected networks is not a good idea for this type of PDE. Right, so I was saying that the number of parameters really increases, and it doesn't increase linearly. It's like increasing really, really fast. And so that is just not scalable. If we go to like omega equals 1,000, like how many parameters are we going to need for a PINN? And the other kind of issue is, even if I model all the cycles here, we see the solution is still not very correct. If you look at the loss, it takes way longer to converge and doesn't converge to like as close to the solution as the simple case does. So we've got lots of kind of compounding problems here, and you can see this is just not going to scale. Okay, so PINNs have we know about these limitations, and there have been many extensions to try and overcome these limitations, and that's what I'm going to talk you through for the rest of the talk. And if you look at the number of citations of PINNs, they've been growing like exponentially since the paper was released. There's now around 4,000, nearly 5,000 citations of the paper. And if you just look at like the top citations, there are like hundreds to thousands of extensions of PINNs. So I mean, if you're really interested in PINNs more, I would definitely recommend. There was this review paper that came out, which is very interesting, tries to cover kind of these extensions, and there are many other kind of reviews as well. Okay, so yeah, we're going to talk about the limitations. So these three different limitations. Okay, so let's go back to the computational cost first of all. So remember that what I said was the biggest problem when you're using PINNs for forward simulation is the fact that you have to retrain the PINN for every new initial condition or new parameter of the PDE. So can anyone think of like ways that we can improve the PINN to not have to do that? How could you change it? Sorry, I can't.
Like the way you sample the points.
Yeah. Where you sample the points. Yes, that is one way. That can help. So if you have less sample points, you can train it quicker, but maybe it would only give you like a 2x speed up maybe. How can you get like a massive speed up? Say, for example, I want to carry out a simulation and I have lots of examples of like the input conditions. Okay, so I'll tell you. So what you can do is you can do something called conditioning of the PINN. And so say, for example, I want to, for this wave equation simulation, I actually want to learn a model that can simulate many different source locations. So I want to shift the location of the source and be able to get the solution at many different source locations. So what I said before is if you just have a standard PINN, you're going to have to retrain this for every new source location. And this source location is like a implicit parameter of your PDE loss. It goes into the PDE loss, or actually the boundary loss, and that's where it's kind of inserted into the training. So the key idea here is very simple: is why don't we just condition the PINN? So add this source location as an additional parameter to the network. So we have this type of network instead. And so what we're going to do is we're going to say, okay, the PINN's going to model the solution. It's still, a function of x, y, and t, but it's also going to accept as input the coordinates of the source, so the x location and the y location here. And I'm going to train this such that once I've trained this neural network, I'm going to end up with a network that I can not only query it any coordinate, but I can give it an input source location as well. And the hope is if I train it well enough, I don't have to retrain it for every new kind of source location. And so this gives me a much faster way to simulate many different sources, simultaneously. Does that make sense to everyone? Yeah, so I call this a condition PINN. Yep.
We have been looking only at autonomous differential equations so far. Does this also work for an input, basically? Can we do the same?
Yes.
Okay.
Yeah, so this is a very general idea. So the general idea is I'll take any initial condition, boundary condition, coefficient of the PDE, whatever you want to vary in the simulation. And we could just insert that as an input to the network, if that makes sense. So at the moment we just got two very simple scalar values, which is just the X and Y location of the source. But you can extend pins to accept more complicated inputs. So for example, we might want to condition on the velocity model itself, which in general is this like function of X. So this is a more complex condition. Okay, so how are we going to train this? This is the next thing. So let's think about it. So we have the loss function for the pin. This is just the same loss function that I've been showing every time. So the boundary loss. And in this example, the boundary is just given by examples of the solution from finite difference simulation from the first time step. So, and then the physics loss is, again, it's queried throughout the domain. Okay, so now we're going to do the same thing for the condition pin. And we're just going to make a few very key changes. And so the first is now the neural network it's the same network, but it has this additional parameter, which is the source location. So I'm just going to add the source location here and the source location here. And then I'm also going to explicitly run an FD simulation, which has the source location labels. So we're going to run many FD simulations. And what's the most important thing here is when we're generating these examples here, remember the loss function is over many examples. And before they were just examples of the points in the domain and the FD simulations. Now we're going to run many different FD simulations with many different examples of source locations and give that to the boundary conditions so that the network learns the general boundary across all different source locations. Does that make sense? And the same thing with the physics loss, where we're going to sample the physics loss, not just in points in X, Y, T space. We're also going to sample random source locations and get the network to make sure the PDE is like satisfied for any source location that it's given inside the domain. So you can think of this as like simultaneously learning lots of solutions at once, like a bundle of solutions where they vary across the source location itself. And because the network is like a good interpolator, it can smoothly interpolate across all these example source locations that you give it. And so it can learn to generalize in some sense to any kind of arbitrary source location within the distribution of source locations that you give it as training data. Okay, so we did this for this wave equation problem. This time we took like a more complex velocity model. It's called the Marmusi model. It's a more Earth realistic model. And so instead of just picking one source location to learn the solution, we generated like many FD simulations as examples of all these white points here in on the plot. So we trained it with all these different source locations and collocation points again across the domain. And then once we've trained the network, we don't have to retrain it for new source locations. And so we queried it on these red points here. So within the kind of same distribution as our training points. And you can see that the pin does learn to generalize to the source location somewhat. I mean, that it's not a perfect solution, and there are other reasons which I don't have time to go into why it's not performing particularly well here. But in general, what it's done is it's learned what we would call a surrogate model of the solution. So this is really cool because we can take this model and then we can go and use it for other applications. So for example, we could use it for inverse problems where we can then say we want to match the network's output to like some observed parameters and try and optimize what the source locations would be, for example. So we can do an inverse problem learning where the source is. And this would be way faster than if we did that inverse problem with a forward simulation, like an FD simulator, for example. Okay, cool. So you can see how this gives you like an order of magnitude jump in the computational speed of pins. So yeah, go on.
I can see that this would be much faster during inputs, but I would also imagine that the training takes much longer than compared to those training for a single fixed source.
Yeah, so you are right for sure. So, and the training does increase, so this is a question of where is it useful to do this sort of upfront cost. So what you can think of as the training is like an amortized cost. It's like one big chunk of cost that you have to incur, and then you have this model forever. So for example, if you're like I don't know, like an engineer, like looking at different models of wings, and you want to figure out the flow, and you do this like every day, just like testing different ideas. You could train one big model, spend like a long time on it, but then you have this model that you can use for the rest of your job. So yeah. Same with like climate simulation, for example. If you want to run a climate simulation many times to like test the sensitivities. So, but if you're just running one single simulation, it doesn't make sense. So yeah, it's a very good question. And what's interesting is, and it is a area of research you can go into, is like, what's really happening here is the PINN is learning to interpolate between your data points, and that's why it's powerful, because you don't have to run a simulation for every single like dense sampled like input. And so that's the real speed up, is the fact that PINN's being able to interpolate the bits that you haven't run a simulation for. Yeah. Okay. So you can, so as I was saying previously, we just condition this PINN on like 2 scalar values, but we can make this idea, we can go to more difficult conditioning. So for example, this is the diffusion reaction equation. It doesn't matter too much what's happening here, but the idea of this problem is to try and condition the PINN on this function u of x here. And so this is now a function, it's not a scalar value. So how do you actually input a function into a PINN? That's actually kind of hard. What you can do instead is just discretize this function. So just take 1,000 samples of this function here. These are example input functions. And so we can just take like 100 or 1,000 like discrete samples of that input function. And so this is what this block of points is here. These are just discretized values of u. We're going to have a neural network architecture here. This is a architecture called a deep operator net. And Sid is going to go into the kind of mathematics behind this and why these types of networks are interesting to study. But for now, you can just think of it as 2 kind of fully connected networks. One that takes as input the x and t coordinates of the domain, and the other one which takes these discrete values of the solution. Sorry, not the solution, of this u of x function. You pass them through a bunch of layers, multiply their kind of hidden representations together, and you get out the value of the solution. So this is essentially a conditioned PINN, as I was saying before, but you're putting in way more kind of inputs rather than just 2 scalar values. And you can train it in exactly the same way, and again, it will learn the solution across these different u functions, for example. So you don't have to you're free to choose whatever kind of architecture you want that makes sense to kind of encode these inputs into something reasonable for the PINN to finally output a solution. And this is a very kind of, again, active area of research. Okay, so yeah, I did actually forget to mention at the start, like all of these, this whole kind of lecture is showing you kind of the latest ideas in research. So these kind of papers and ideas have only come around in the last couple of years. So everything here can be built upon, and these are kind of just ideas for you to take away for sure. So, okay, so this is another different way to try and speed up PINNs. And so I call these discretized PINNs. And so one of the big limitations of PINNs so far is we've just been using fully connected networks. And I tried to show you before with that sinusoidal problem, a fully connected network is not actually a good idea. It doesn't scale to like higher frequencies. So another idea is, well, we know that our solutions here that we're trying to model have like lots of spatial correlations. Like they're not random like pixelated images. There's like lots of nice spatial correlations here. And so why don't we use like convolutional networks, for example, which we know are really great at learning like spatial correlations between its inputs and outputs, to try and, as a better kind of inductive prior, as a model that's more efficient at representing the solutions or the types of solutions that we want to output from the PIN. But there's a kind of challenge here, is like, if we use a convolutional network, like how are we going to get a solution like a single value? So remember the fully connected networks here, they produce like a scalar value, which is like the pressure, for example, as a function of the input coordinates. If we're going to have the output of a convolutional network, this is generally like an image. It has lots of points. So the idea here is, okay, we're just, instead of using this like continuous representation of the solution, we're going to go back to using like a discrete representation. So we're going to say, I want to learn the solution on a grid. So this is, again, the Burgers solution example. And I'm going to have just a standard convolutional network, and the output of the network is just going to be a matrix of values, which is just the discretized solution. So it's going to be like 128 by 256, for example. So that's the output of the ConvNet. So yeah, we're going from this like functional representation of the solution, which is the PIN here, to this discretized representation of the solution here, where each output of the network is just like a single value of the solution. Okay, so we're taking that hit, going from continuous to discrete, to be able to use like a ConvNet architecture to represent the solution. And so the inputs of the network for now, we're just going to say it's just a fixed value. It's just going to be 0. So just a scalar value. And we're going to use these transposed convolutional layers, which essentially just expand the image, grow the image outwards, or the output of the network outwards to get this 2D matrix. Okay, so why are we doing this? So let's think about how could we train this ConvNet to actually learn the solution here? Because before it's trained, it's just going to give a random output. So how do we do it? So we're actually going to train it in exactly the same way that we train a PIN. So before, we had the PIN has this physics loss here, which operates on the output of the network. We're going to do the same thing with this discretized PIN. We're going to have the outputs in the network, and we're going to create a physics loss function, which is going to get derivatives of that output, spatial derivatives and time derivatives, and we're going to try and minimize those such that the PDE loss is like minimized. And you can see, analogous to how a PIN works, this is going to try and learn the solution as on this output mesh or this output grid. Okay, but the key question here is, how do we actually evaluate these derivatives, like dn by dt? T is no longer an input of the network, so we can't use like auto differentiation to get a derivative of the output with respect to its inputs, because it's just not an input of the network. T instead is like this axis of the output array, right? Because it's a discretized solution. So to evaluate these derivatives, we're now going to use finite differences instead of autograd with respect to the inputs of the network. So it's very simple. If this is just a mesh of points, and so if we want to estimate what dn by dt is at this particular grid point, we're just going to take differences whether it's neighboring grid points. And you can see how that would give you the derivative, an approximate derivative of the solution. And so you can do the same thing for dn by dx and dn by dx squared. And you don't have to use one point. You can use like higher order estimates of the derivatives if you fit like polynomial functions, for example. Okay, so then it turns out if we just do that, and we train the network, we can get the network to learn this solution. And that's actually really cool, because we're not giving it any simulated data or anything like that. It's doing it in a fully unsupervised way, just how a PIN is also an unsupervised way of learning your solution. So it's a really cool idea, and it lets us use these ConvNets to learn solutions that are like to exploit spatial correlations. Yeah.
This destroy the main advantage, which is you don't need the mesh.
Yes, absolutely. Yeah. It's a balance, or it's a choice basically you have to make. Do you want to use a mesh and use like a network that has like spatial correlations and is like fit towards that type of solution? Or do you just want to use like a fully connected network and have a mesh-free solution? And it depends on the PDE and the problem that you want to solve, whether that's a good idea or not. Yeah, go on.
Did it also get affected by like multi-scale features that we have?
Yep.
Like the problem that we have with mesh.
Exactly. Yep. So for sure, you're seeing all the analogs to like finite difference simulation, finite element. If this mesh is not fine enough, then you're not going to model the higher frequencies, and you'll probably get aliasing and issues with your finite difference estimation as well. Yeah, exactly. These are really good observations. The interesting thing though is that we're still using to update the values of the network, these theta values. We're still going to use auto differentiation. That's going to auto differentiate through this loss function here to update the values of theta. So that auto diff is still used in this problem. So another way to think of it is you can just think the convolutional network is just fitting a function onto this mesh. It's like a function on the mesh kind of. Okay, so I haven't talked about boundary conditions. So remember in the physics, in the PINN, we have this extra loss function. Oh, sorry. I haven't put it in, but in the PINN, we have the boundary loss term to assert the boundary conditions. So we could also have a boundary loss term in this problem. We could just say, you know, the values on the mesh along the boundary should just equal these values and have that as a loss term. There's a kind of more clever way of doing this. It's just to fix the values. So you can just, you know, inside PyTorch, if you get your output array, you can just insert proper values into that array that you know the boundary is, and then they're kind of hard constrained, and you don't actually have to have a boundary loss. So it's just done by appropriate padding of the inputs. Okay. So what's cool is that you can take these networks and then you can start doing conditioned versions of these, just like we had conditioned versions of the PINNs. So remember the condition PINN, we took like initial conditions and we put that as extra input parameters. We can do exactly the same with this discretized version of the PINN. So instead of before we had this random value that it was just a fixed value as input. Now what we can do is get rid of that fixed value and we can just input like these parameters, these like initial conditions or parameters of the PDE. So for example, with the Burger's equation, I could input the viscosity as a thing we want to condition the network on. And maybe also like the starting initial condition of the solution. So like x is so u at time equals 0 is sine x, for example. We could have like a sine wave that we input as the input here, and we could change that function. And so how do we change? We had this discretized loss function that we had before. So how do we change that? Well, it's exactly the same way that we did for the PINN when we changed the loss function to a conditioned loss function. We just add this extra summation over lots of examples of these conditioning inputs. And we sum the loss function over all those examples so that the PINN sees lots of examples as the input. And you can see how the neural network now has you know, our conditioning inputs, and it will give us another surrogate model, which doesn't have to be retrained for each new simulation. And so it's very analogous to how the conditioned PINN works. And you can see that this is also going to be very fast once it's been trained, very similar to the PINN. So yeah, this is a very influential paper in the field. I definitely recommend reading it. They basically introduced this idea and applied it to Darcy flow. So they're doing exactly what I just described, this like conditioned discretized PINN, and they're using this convolutional network just as I showed. And the input is so the idea here is to solve what the fluid flow would be through this. So this is like a channelized system. So this is like underground. You have like these like sandstone channels that the fluid can flow through, and then around it is just these areas which are completely impermeable, like granite, for example. And say if you have some flow, like pressure difference between the two, you'll have some flow. So if you have a pressure difference between the two sides of this block of earth, for example, you would have some flow through these channels. And the goal is to predict like what's the flux and what's the pressure distribution across this area. And so this is just given by like Darcy's law, Darcy's equations. Again, I don't need to go into the PDE exactly, but it's the same thing is true. We have the physics loss here, which is just computed on these discretized outputs. And they're doing this separate boundary loss to assert the boundary conditions. And yeah, you train it, and you train it given lots of random examples of these different like channels, so like randomly varied channels as input. And again, as I said before, you don't need any training data for this, so it's fully unsupervised, and it only requires like many examples of these different channelized systems, and it will start to learn the flux or the fluid flow as output. So they do this, and yeah, you can see it works really well. So you give it a different channelized system as input, and it's able to predict fairly accurately compared to like a ground truth simulation. So if you go back to this model, you could think of a very naive way to train this model, which would just be to generate like millions or thousands or millions of examples of simulations. So you could run like simulations with many different examples as inputs, and then just train the network in a very naive sense, which is just fully data driven. So, you know, just a supervised loss function, which says I want the outputs to match the outputs from simulation. Now that is much harder to do because you have to generate thousands of example simulations. And if those simulations are really expensive to run, then that takes a long time to train it. But they did this because they wanted to compare this, like, you know, the physics informed, the discrete PINN versus like that fully data driven trained CNN. And you just keep the architecture exactly the same. So the only thing we're changing is the loss function and the data that it's trained on. And what's really interesting is you see that the data driven one does improve somewhat, but because you rely on so much more data, you know, the PINN is still performing like similarly. So like it's a really interesting way of getting rid of the training data is to add this physics loss instead. What was more interesting is they actually tested the generalization of the network. So this is where you give like an example input that's not a channelized system. So it could be something else that's like a different permeability field that is not inside of the training distribution. And they found that the physics constrained network actually did better on those, like as learned to generalize better. And so that's really interesting too. Okay, so let's just summarize these discretized PINNs, because that is quite a whole subject in itself, and there's been a lot of work in that area. And it's kind of as you were describing, there are advantages and disadvantages that you need to think about. So the advantage is that yeah, they allow you to use these CNNs to like exploit the spatial correlations in the solution. So you have like a better inductive bias of the network. They are fully unsupervised, so you can train without any data. And I haven't put it into this lecture, but you can also extend them to other networks. So you can use, for example, graph nets if you want to go from a regular mesh to an irregular mesh. You can also encode, like for time-dependent PDEs, you can actually encode like an explicit time dependence by using like a recursive neural network to model each time step. And you can even do really exotic things, like, for example, have some of the input coordinates be continuous. So you learn like a continuous function on some coordinates and a discrete solution on other coordinates. And that's a very interesting area. Yeah, but on the limitations, it depends on the mesh. We have to bring back a mesh. We're applying on approximate FD gradients, et cetera, et cetera. So. Okay, there is one more thing on the computational side before we take a little break. So this is one other way to train PINNs. And so this is going back to the computational cost of evaluating the gradients of the network when you're training it. So we're going back to training PINNs now. As I said before, most of the time is spent computing those gradients rather than the forward pass of the network. So one idea is to, you know, still have the same PINN, same neural network, same loss function, but instead of using autograd to get those gradients of the physics loss, we'll just approximate those gradients with finite differences instead. So this is not the discrete PINN. This is just using FD gradients to evaluate its loss function. So for example, like, you know, if I have my neural network here, which is a function of the input coordinates, the m by dx, we could also we could run the network forward for 2 points with a small displacement a, and then just get the difference of those to approximate what this gradient is. And so then we don't have to use autograd to get this derivative, but it is at the expense of having to run the network forward with 2 points rather than 1 point. And so you find that this can offer you generally 2 to 4 times speed up, maybe even more depending on the problem. Yeah, and in general, what you do is for each of your collocation points, you'll create like a stencil, an FD stencil of input points from that. You'll run all of those forwards, compute a derivative based on the outputs of the network, and then use that inside your loss function. And again, you're still going to use auto differentiation to update the weights of the network with that approximate loss function. But again, like choosing the value of A, how close these points are together is really important choice. Okay, I think we'll take a short break and then we'll get back to the next two. Yeah.
Just to some part physical, but to some parts you have like uncertain. Let's say whether that we don't measure the winds.
Yeah, I think things that this is where they're best. These types of problems which are like where you have some understanding of physics, but not every
okay,
and you have like some observation data. Yeah. So it's kind of like a forward problem where you want to simulate the solution. You also understand this parameters of the PDE. Okay. So what you would probably do is then you know something about PDE, and maybe forcing to source code, whatever, something inside which is approximately that thing with like either just a single value or like another network. For example, when I was talking about PINNs for input, we have like a separate network that runs the velocity. Yeah. So yeah, you train this and we'll join it together in one big organization.
Okay.
And yeah, generally they'll competitive to other like traditional methods. Okay. But this type of stuff is like it's only been researched over the last 2-3 years. So yeah, it's very much an open question.
Okay.
How it works properly. Okay. In general, that's the case. Okay. Yeah. Have you got a particular problem in mind?
Yeah, I'm currently working with aircraft, and especially with aircraft flight.
Okay.
And
yeah,
the point is that it highly depends on weather and wind, on temperature and winds, and on air traffic controllers, controls.
Yes, yeah.
And somehow, for sure, the client is somewhat described by the differential equation and the harassment and stuff like that. But there, it feels like to me when I look at the data, there's more uncertainty than physics, and that somehow
yeah. So you would need to, you could definitely, that would be a very interesting problem to want to use PINN one. You would write down what you think your equations are. Yeah. Then you would also have to think like, what am I certain about, and how can I make that like a mathematical expression that is flexible that I can learn bits that I don't understand.
So in some sense, if I have the differential equation for whatever the client, and I feel like temperature is one of the big factors, I just add this as an unknown.
Exactly. Add that into an unknown initial equation and add it, and then learn it until the end. Like a learn how that.
Okay. And then my guess would then be where to put it exactly.
You would have to use your like mathematical intuition to figure out where is it sensible to put that into the PDE somehow.
But this even when the temperature is not measured. So let's suppose I don't have those measurements, or I don't have particular measurements, it even works in those things.
Yeah, possibly. I think maybe we could meet afterwards. You could show me like the problem.
Sure, I will love it. Okay, cool.
Maybe I would better. Okay, how's it going?
Sorry, I would like to ask what does source location mean in conditional PINN?
So the source location is when I'm doing the weight equation.
Yes.
And I have that point source.
Okay.
That's exploding outwards. I'm trying to simplify. The source location is just the location of that.
It's like the initial condition, different kind of initial condition.
Yeah. So if the point source starts here, then the source location is x and y coordinate.
Okay.
And that is like a initial condition
Okay, thank you very much. I don't really understand this terminology.
Makes sense.
Yeah, thank you very much. And another thing is that if we the point we use this discretized PINN is for convolutional layers.
Yeah.
Then does it works if I just like use normal PIN without discretization, just change the layers into convolutional layers?
Yeah, you could.
And then I just
You
like
could, yeah.
vectorize it or like
Yeah.
sum it up. Okay, lightning.
Yeah. Flattening.
Yeah, into
Yeah, so that's the challenge. So you're starting with just your X and Y and T, which are 3 values.
yes,
You'd have to expand that somehow into an image, then do like a convolutional layers,
yes.
then reduce that back into like a single value, which is the solution. So, and I've never tried it. I think it could be interesting, but it's tricky because your input is not like an image anymore. It's just your points. And the output is not also an image, it's just a single scalar value. So
Yes, but isn't this some kind of thing that they do in image classification, like they do convolution?
yeah, no, you're right. You are right. Yeah, it's how classification works. And you have basically have a coordinate and then a fully connected together, and it just gives you a single value. So yeah, I'd love to see that test. That'd be interesting.
Okay, thank you very much.
Yeah,
Just asking.
yeah.
Yeah. And also, sorry, another. Sorry.
You can also ask at the end of the lecture.
Okay.
We'll do that. Yeah.
It does have a question regarding this function u of x that you added, basically.
Yeah.
Is it the fixed function which is predefined, kind of, or is this an arbitrary function?
So it's an arbitrary function. It's like a initial condition of the PDE.
Yeah.
And so we just discretize that and add that as an input to the network.
Okay, so I can choose any.
And you could choose any
value.
yeah.
Okay.
And you sample lots of those functions with training data when you're doing the deep learning. Yeah.
I was just wondering, we had this case where we had different sources.
Yeah.
We said we could just train them with all different sources.
Yes.
Yeah. We also do transfer learning.
Yeah.
Does that work? Or
Yes.
is it something like-
Yeah.
So-
Yeah, so you could train on a set of source terms, and then if you're given like one that's way higher, or like further away in the domain that you haven't trained on, then you could just transfer them the PIN and you would train it with compared to and people have done that as well actually. But for like nearly Stokes equations, for example, if you want to learn the different SSD parameters, use the evidence and sort of stuff.
And it's kind of fine tuning to this.
Yeah, it's fine tuning.
for
Yeah.
it. So, okay.
Yeah, and it works. So it does work.
Thank you.
Okay.
For this word, I think it can lose the advantages of processing higher dimensional problem. Like
Yeah.
if you use this way to calculate the derivatives.
Yeah, it could also help like higher order gradients because they're very expensive to compute. Like
Yeah.
if you want dn by dx to the 4 or something.
Yeah. And we also use the curse of dimension.
Yeah, I'm not sure about that. Yeah, because you would have to have a stencil that's many more points.
Yeah.
So I'm not sure about that. Yeah. Well, I'll think about it. I'll let you know. Yeah.
Thanks.
Okay. Okay, everyone, let's get back to it. So we're going to talk about the second limitation, which is the convergence of pins. So we were talking about computational cost before. And we had this issue that I was describing where we have these two different terms in the loss function, the boundary loss and the physics loss, and they can compete because they have different objectives that they're trying to minimize. Okay, so one idea that we can do, we want to try and improve this situation. And what you can try and do is get rid of the boundary loss entirely and try to make the pin so that it always satisfies the boundary conditions, no matter what the physics loss is doing. So we call these like hard constraints, like hard initial and boundary conditions. And there's a really key idea for doing this, and this is one way of doing it. And this idea is to use the network as part of a solution ansatz. Hopefully you've heard of ansatz before. This is the idea where you like start off with like a mathematical expression that you think might like represent the solution to something, but you're not entirely sure. So it's like a starting guess. That's what an ansatz means. And so again, let's just take this Burger's problem that we've been studying throughout the lecture. And so now, so what we had for the PINN, a vanilla PINN, is we said the neural network should directly approximate the solution to the differential equation. So neural network should equal or approximately equal u of x and t. So what we're going to do now is something very slightly different. We're going to say our solution u of x t here is not approximated directly by the network, but it's approximated by this mathematical expression which contains the network inside of it. So in particular, so we're going to call this expression an ansatz, and we're going to say this is approximately equal to the solution. And we're going to pick this expression, and what's the clever kind of trick is that we can pick these expressions such that the boundary conditions are always obeyed. This ansatz always obeys the boundary conditions. So for example, we can say neural network here, we're going to times it by t minus 1, x plus 1, x minus 1, and then we're going to subtract sine pi of x from all of this stuff. So then we're going to train this. We're going to train this instead of just the standard neural network. And what you can fairly easily see is no matter what the neural network learns. So the network here could, in general, it could learn any function, any arbitrary function. Whatever it learns, this ansatz is always going to satisfy these initial conditions. So let's test it out. So for example, we want to make sure the ansatz at time equals 0 is always minus sine pi of x. Okay, so let's put in t equals 0 into this solution. T equals 0 here is going to make this term 0, and it's going to cancel out anything that the network learns here, and it's just going to end up with sine pi of x. So you can see whatever nn is here, sine pi of x is always going to be true. And the same with these initial conditions here. If x is minus 1 for all of t, x is minus 1 here, again, it's going to zero out this. So this can be 0. And sine of x at minus 1, sine pi of x at minus 1 is also 0. And so again, this ansatz is always going to satisfy these three different conditions that we have. So we call this, satisfying the conditions by construction of the ansatz rather than using it as a inside the loss function in the network. So this means we can just throw away this boundary condition, and we just use this single physics loss as our entire loss function. And instead of having the neural network inside the physics loss, we're having this ansatz inside the physics loss instead. So we're substituting this expression into the loss function. And this essentially turns this optimization problem from a constrained optimization function where the constraint is the boundary conditions to an unconstrained optimization problem where you're just trying to minimize a single loss function, a single term in the loss function. So we can think of this as this expression here. This is just a bunch of operations on the network. And you could just think of that as like a custom final layer of the network that you're just applying a couple more operations to. So you could think of this whole thing as just one conglomerate of a network. And you can think of that custom final layer as just like a hard constraint on the network's output. So like a physics-informed architecture even. And we can just differentiate through that final layer, through the expression, just using autodiff, just as we do with the neural network operations. And it's become fully unsupervised as well, because we don't have to have these examples of the boundary. It's just already encoded into the network. So it's a really powerful idea. The hard thing is to actually come up with this expression yourself. And this can be very hard to design by hand, especially if you have way more complex boundaries like irregular geometries and higher order derivatives of initial conditions, etc. So there are ways to get around it, but this is the general idea. So you can do this with for example, trying to solve the incompressible Navier-Stokes. So this is just trying to model the fluid through a pipe that is just compressed in the middle. And so the color of the simulation here is just the speed of the fluid. And so as you get compressed, obviously the fluid speeds up to conserve mass and continuity. And what we find, what these authors found, is if they trained a standard PINN, so this is with the boundary loss and the physics loss, the PIN just doesn't manage to converge. And it's probably because of this competition between these two loss terms. And they tried it with these different, lambda values, like balancing the different loss terms differently. And they still couldn't manage to make it work for this problem. But if you do this approach where you put a hard constraint in the boundary conditions, and so then you only have the physics loss, the PIN does seem to converge for this problem. And so you can see how the optimization problem is made slightly easier because we have these hard constraints. Okay. So yeah, that can be challenging to do, especially if you have irregular geometries or really hard boundary conditions. So another idea is to, instead of us trying to pick these lambda values as a hyperparameter, and typically what you would do is just train the network many times, scan through different lambdas, figure out the one that has the lowest test and train loss, for example. Another idea is to treat those lambda values as actually learnable parameters. Can we actually learn the best value of lambda that minimizes the total loss best? And so, yeah, there's this idea that just came out, this year or last year, called self-adaptive physics-informed neural networks. And so this idea is, instead of having a single lambda value for each loss term, we have a single lambda value for every single collocation point in the domain. So lambda here now is indexed by kj. So these are all the boundary conditions, and also by I, so all the collocation points in the physics loss. And we're going to learn these in our loss function as well as theta, and we're going to do it simultaneously. Okay, but I mean, an obvious way to minimize the loss function with lambda is just to set lambda equals 0. So that's not going to work if we just naively minimize the loss function. So what they actually do, instead of minimizing when you're training lambda, when you're updating lambda, you actually try to maximize the loss function rather than minimize it. Okay, so why would you do that? So yeah, this is the training loop. You compute your gradients of your loss, update your weights just as you would normally do, minimizing the loss function, and then update the lambdas by maximizing the loss function rather than minimizing it. Yeah, so why is that an interesting idea to do? Well, if you think about it, let's think about dl by d lambda. If lambda, it's just a partial derivative. So if you just think about the loss function, dl by d lambda here is just my PDE residual. It's just the residual of the differential equation. So what this is saying is, if my residual at that collocation point of the differential equation, if the residual is high, basically the network at that point is not fitting the data very well. When I update my lambda, I'm going to make it larger. So I'm going to say, okay, I've realized that at that particular collocation point, you're not fitting the solution well. I'm going to increase the weight of that collocation point so you focus on it more in the next training step. Does that make sense? So then somehow the network and optimizing lambdas is learning to focus on the parts of the solution that are hard to converge in terms of the physics loss, and also in terms of the boundary loss, because we do the same thing with the boundary. Okay, so from a kind of pure machine learning sense, you can kind of think of this as an attentive layer, it's attending to the parts of the solution that are hard to converge, for example. A bit like how transformers, as I was showing you in ChatGPT, attend to different parts of the input sequence. So yeah, you can train it on the Helmholtz equation, for example. This is just the vibration of a plate, for example. And you can look at these final lambda values. Remember the lambda value for every single collocation point and boundary point. So you can just plot them. And you can see what's interesting is the lambda values here are higher for where you have these high amplitudes of the solution, and basically 0 where the solution is 0 already. So maybe the solution here is what it's saying is the solution is maybe easier to learn where it's 0 here and harder to learn over here. And so we have to focus on these parts of the solution. So yeah, it's a cool idea, and seems to work for some of the problems they show in the paper. So okay, this is a suggestion that someone else gave. So changing the collocation points, and this is a really big factor actually for the convergence of PINNs. And your choice of these collocation points really affects how they converge. And what we often do to make it easy is we just say, okay, we're just going to uniformly sample our domain for our collocation points. Or you might do like a random sampling or a grid, for example. That can work okay, but it's not actually the best choice. There are other choices that you can make. And you can actually be a bit more clever about this and say, I'm going to adapt these collocation points depending on how well my solution is converging. So for example, this could be any PDE, but what we're plotting here is the residual of that PDE. So how well the network satisfies the PDE over the domain. So you can see the network is like solving well around the edges, but in the middle here, it's really messed up the solution. So the residual as a function of the coordinates here is very high. So a natural idea would be, okay, I'm just going to sample my collocation points more around here to try and make sure that the network learns a good solution here. It may be, for example, that the collocation points are not finely sampled enough if the solution here is very high frequency, for example. So instead of having uniform sampling, we might like do this more dense sampling around where the residual is high. So yeah, the idea is very simple. We just say, when we're picking collocation points for each training step, we're just going to sample according to this probability distribution, which is just directly proportional to the PDE residual function itself. So yeah, this is just the residual here. It's just, you know, the PDE residual. And A is some normalizing constant. So we're going to have to normalize this over many inputs to sample from a distribution rather than just a function. And you can see how this is kind of like analogous to adaptive mesh refinement, where, you know, in finite element methods, where again, you're making the mesh smaller where you know the solution is like higher frequency or more complex. So again, this is another study that just came out very recently. And it is a fairly comprehensive assessment on all these different strategies for sampling collocation points. And they compared these like simple uniform sampling with these adaptive refinement methods. So for example, this one. And they tested it over a bunch of different equations. And it's quite interesting, actually, the difference they get from these different collocation strategies. And what I found interesting is it seemed like just a standard uniform sampling seems to be actually the worst choice for across these tests. So for example, the wave equation, this is the 81% error, for example. So lower is better here for in the table. Yep.
The sampling points with every
Yeah. Yeah, so this is totally up to you. This is a design choice. You can either do it every single training step and adapt, or you can say, I'll do it every 1,000 steps, for example. It depends how computationally expensive it is to actually evaluate this distribution. It can be quite expensive because you basically got to, you know, measure the PDE loss very densely across the whole domain. So it's actually quite expensive. Yeah. So they found these residual method adaptive refinement methods to be the best for these particular problems. So what do these other sampling methods look like? So this is grid. Then you have like random or pseudo-random at least. And then you have these other ones which are like quasi-random, which try to make sure you sample like most of the space, but in like a quasi-random way. So you can go into exactly how these methods work in more detail if you're interested. But, yeah. So we just had a break already. So I'm going to try it. If we don't have enough time, that's fine. Sid will carry on next time. So the final one is scaling to more complex problems. So we've covered the computational cost, changing the loss function to try and converge better. So let's think about scaling. Okay. Yeah, so let's go back to this issue that I showed you at the start. This is the problem that if I just do a fully connected network with a cosine or a sine solution, increase the frequency, the PIN just doesn't scale. We need way more parameters. It takes longer to converge, and it doesn't converge to the same accuracy as the simple solution. So how do we change this? Okay, so this is related to this issue, which I think I mentioned in a couple of lectures ago, called the spectral bias of neural networks. So this is the observation so this is not doing physics-informed networks anymore. This is just supervised training. So just trying to fit a neural network to this very multi-scale function here with high frequencies in it. And it's just the observation that as you train the network, it tends to learn the lower frequencies much faster than it learns the high frequency components of the output. This is known as the spectral bias. Under certain assumptions, it can actually be the convergence of the different frequencies can be proved under neural tangent kernel theory. And so this is a really interesting kind of theoretical analysis of neural networks, and I definitely recommend having a read of these papers if you're interested. And so this is why early stopping works. Do you remember we were talking about regularization of neural networks? And if you stop the neural network before the test and train losses diverged, then you get a nice generalizing model. And it's likely because the network has fit the low frequencies and not overfit to the data and added higher frequencies that start overfitting your training data. So for example, here, if you stop training here, maybe that's a more general model than if you had like high frequency fits, for example. Okay. So this is basically happening in here. We as well as having this expressivity issue where we need more parameters, we also have this spectral bias, which is making the problem even harder on top. Okay, so how do we overcome this? So we need to think about changing the architecture of the network, having a better architecture that has a prior or like a bias towards the types of solutions that we actually want to model given the PDE. So let's just assume that we have like high frequencies in our solution rather than low frequencies. So one idea is to use, which is popular, is to use these things called Fourier features. So it's actually a very simple idea. And the idea is, so the input to the pin is just our input coordinates here. And the idea is to transform these input coordinates to higher frequencies before we pass them through the like hidden layers of the network. So what's the actual transformer we use? It's just these cosines and sines of x. And this just turns into a bunch of hidden features that we just input to the hidden layers of the network. And so gamma here is a matrix of shape KD, where D is the dimensionality of the inputs, and K is the number of features, the number of transforms that you want to do to these inputs. And so typically your sample, so gamma here represents the frequency of each feature, and you might sample those frequencies instead of just having a single frequency feature. You might have like 10 or 20 or 100 different frequencies that you transform over. So you start with a range of Fourier features. And typically we actually draw these values from a normal distribution where mu and sigma here are some hyperparameter choice that we have to make. Like we want the inputs to generally be over this range of frequencies. Okay, so the idea is to like already transform it into like a high frequency kind of representation somehow, such that the solution is like a bit easier to learn in some way. It's kind of hard to figure out like intuitively what's going on though, because once you've transformed these features, then you're passing them through all these weird like activation functions and linear layers. It's actually kind of, I find it intuitively hard to understand what happens afterwards. But if you look empirically, if you do this, now we're using PINNs to try and solve the Poisson's equation just in 1D. But Poisson's equation is interesting because you can have solutions that are very multi-scale. So for example, the solution here can be like a sine wave that's riding on another sine wave, which is much higher frequency. So you basically have like a multi-scale solution here with two different frequency components. And if you train the PINN on this one, it's the same story as what I was showing before, like a vanilla PINN just doesn't converge. And then if you do the same PINN, but with these Fourier features, and here what they did is they did two sets of Fourier features where they had different frequency contents, like trying to honor the fact we have two different scales in the solution here. It seems to fit much better to the data. Yeah, but I mean, there's an obvious caveat here is that you have to choose these gamma values to try and match the solutions inside that you expect. So there's not really a free lunch here. It's more that you're choosing a network function that better approximates the solution that you know should exist. So these types of Fourier features actually came from like computer vision and were used to like model like high frequency images, and they turned out to be very good at like generating high frequency images rather than like smoothed images. Okay, and so the next idea is to use domain decomposition, and so this is something that I've been working on in my own research, and it's the idea here is to use to become inspired by like finite element methods, finite different methods, where we chop up the domain into lots of small pieces, into lots of subdomains. And so the idea is, can we do the same thing with PINNs? And instead of trying to have one neural network which learns the entire solution, which could be very, very complex if you have a really large domain with lots of frequencies in it, can we have like lots of little neural networks which learn small solutions inside little subdomains? And then can we like combine them all together to get our final solution? And the kind of intuition here is to like use a divide and conquer like strategy, where to solve the one big optimization problem is really hard, but maybe we can turn it into lots of small optimization problems where each neural network learns the solution in its own little area. And maybe that's easier to learn than the large PINN itself. So what we're going to do is we're going to have, instead of one neural network learning the solution to this, so this is du by dx is cos omega x, the same problem before. And instead of having one large neural network, we're going to have 1, 2, 3, 4, 5 different neural networks here, each in its own little subdomain. And so we're just going to choose this like arbitrary, for now, just an arbitrary definition of the subdomains, and we're going to make sure they overlap a little bit as well. And this overlapping is really important so that the networks can like communicate with each other and make sure that their solutions match across their boundaries. And then the other thing we're going to do is each neural network that we're going to place in one of these subdomains, we're going to we have to make sure that that network is restricted to that subdomain. It doesn't have values outside of it. Otherwise, that would kind of defeat the object of the domain decomposition. And so we're going to take the network's output and we're going to multiply it by a window function. And that makes sure that the network's solution is just 0 everywhere that's not within that window, within that subdomain, for example. So you would hope that the networks, if you train this domain decomposition well, the networks would learn these types of solutions, for example. And then so the idea is if we sum all of these neural networks together, then we get the final solution. So what does that look like mathematically? So remember we were talking about these ansatses, where you have, instead of the network equaling the solution, you have the network as part of some mathematical expression, and that equals the solution instead. It's exactly the same idea here. We say now our solution of the PDE is now a summation over all of these different subdomain neural networks, neural network I here, and that's the total solution. And they're times by these window functions to make sure they're constrained within each of their little subdomains. Cool. So that's the idea. There are 2 other things that happen, and this is just basic normalization and unnormalization of your inputs and outputs in the network, which is just standard. It's just a standard thing that you should do for neural networks, is to make sure their inputs are between -1 and 1 and outputs. But what's interesting is when we do the input normalization of the network here, we do it for each subdomain individually. So for example, this neural network here is normalized between its subdomain boundaries, so between this value and this value. It's not normalized between the whole domain. And what this actually does is it actually reduces the effective frequency that the network's seeing of the solution. Instead of it being like a high frequency solution that it has to learn, because it's been normalized between its own, just by its own individual subdomain, it effectively stretches the frequency out and makes it a low frequency problem that it has to solve. And so this is actually a really important trick that reduces the spectral bias issue that I was talking about before. Each neural network here has to learn a much lower frequency solution than it would have had to do if it had to learn the entire solution. So yeah, you can do this for this high frequency sinusoidal wave. And so we're just going to have a domain decomposition now, which has, I can't count exactly, maybe 15 or maybe even more subdomains. And we're going to link them together by just summing all the networks, timesing it by a window function, and training it. Yep, cool. Yeah. Yeah, so what we can do, because this is, so you can think of this, it's just an ansatz, just like it was. Yeah, like the hard constraint. Yeah, kind of. This is just an ansatz. So you can think of this as just a fancy neural network architecture. Like this whole thing is just another architecture, which takes in an X and outputs a single value. And it's got lots of neural networks that are all communicating together and like producing a single value. So if you just turn that into a black box, then you've just got a same setup where you have a neural network as a function of X, and then you train it with exactly the same loss function as a PINN. So you have the boundary loss, the physics loss, or you can add these hard constraints on top if you want. So this is what this C thing is here. It's adding these hard constraints on top. So yeah, from the perspective of training it as a PINN, it's exactly the same procedure. What's actually happening is, yeah, each neural subdomain network does need to communicate its solution outwards to make sure it has its own little boundary conditions in its subdomain. And it just does that by the way that inside its overlapping regions, you're summing the solution together. And then when you differentiate through those summations, the gradient flows through both networks, and that's how they communicate. Does that make sense? Yeah. Okay. There are other ways to do domain decomposition with PINNs. Another popular method is called XPINNs. And they actually don't have overlapping subdomains, and instead they have additional loss terms which communicate the solutions at the interfaces. So it's actually a more complicated loss function, but a different way. Yeah. Say again. Yeah, so C here would be like those hard constraining ansatzes. So you might times it by like t minus 1 to get its 0, t is 1, or whatever you want it to be. Yeah. Right, so if I train this, so here I've handpicked a domain decomposition where each subdomain is a single cycle of the solution, but it doesn't have to be that way, but I've made it simple for this example. Yeah, and you train it just as you would train a PINN. It's just a custom architecture in some way. And yeah, because it's taking this divide and conquer strategy, and it's also doing this individual normalization of the subdomain networks, it does seem to converge much better for this problem. And I did compare it with these Fourier features as well, just to make a more fair comparison, and it seems to outperform it for this problem as well. Okay. Yeah, and then the natural idea would be to like extend this to like higher dimensions. And so yeah, I've done this as well. So in 2D you would have lots of boxes instead of single lines. And the same idea, you have a neural network in each subdomain, and you make sure the subdomains are overlapping. A kind of thing to remember is as you go to high dimensions, you can start getting more and more overlapping networks. So here you would have four overlapping networks instead of 2. So this is maybe a limitation of this method, is it doesn't really scale to high dimensional PDEs, but it is useful for like 1 and 2D, 3D dimensional problems. Same thing, have a network in each subdomain, do the normalizations, times it by a window function, sum it all together. And it doesn't have to be a rectangular subdomain decomposition, it could be anyone actually. Yeah, so we did that for the wave equation problem that I showed before. Remember, this is the problem that started to thrash when you had the standard PINN. So it converges quite nicely. So what's interesting, and the way that we actually train this, because we have these subdomain networks now, we can start doing all sorts of different training strategies. And in particular, what we can do is we can play around with like the networks that we actually train at each training step. So we don't have to train all the subdomains at once. We can actually switch some of them off and just have, for example, the subdomains at time equals like 1 to 2. So the first time step. And we can just train those first and then fix them and then train the next time step. And then we can train these domain decompositions in like a time stepping fashion, more similar to what you would do when you're solving like a finite difference solver, for example. So that's actually how we train this. We only train the first couple of subdomains here, first time steps of subdomains, made sure that it converged, and then learned the solution outwards by time stepping those subdomains. And you can see that the pin, so we call these finite basis pins, FB pins. And the FB pin like learns the solution outwards in a nice like a stable fashion. So, you know, learns the solution from the initial conditions outwards. Whereas, as I was saying before, this pin thrashed up until like 20,000 steps and then eventually converged.
What do you choose to domains?
Yeah, so this is, again, this is a limitation that you have to know something about your solution, just as you do in finite element methods.
Like a man.
Yeah, you choose the mesh. Although the latest research, and I mean, we're looking at this at the moment, is to actually learn these domains as you're training the pin. So you can parameterize your domain decomposition and then learn those parameters of that. And so this is like a hot area of research right now. Yeah. Yeah.
How does the training time compare?
Training, yeah, so there's a lot more, because you're adding complexity into the architecture, there's many kind of tricks that you can do. You can parallelize the training, for example. So you can feed in, as your compute, you can compute each of the outputs of the network in parallel, for example, and that speeds it up. So the training time is very comparable, actually. In fact, it can be faster because you only need much smaller neural networks inside each subdomain. Whereas with a large pin, I needed like 6 layers, 128 hidden units or more. So yeah, we can go into that. There's a lot more to say about that. Okay, cool. So we've covered a lot. I think I've tried to convince you there's major limitations of pins, but also a lot of really exciting research, which is starting to overcome them and really make them applicable for many different types of problems. There's also a whole bunch of other extensions of pins in the literature that I just haven't had the time to talk to you through. But very briefly, we've been talking about partial differential equations for the most part. There are also other types of differential equations like fractional equations, stochastic PDEs, weak formulations of your differential equations as well. Pins can be adapted to all of these settings. I haven't even talked about uncertainty estimation, but you can actually use pins to get the network to be uncertain about the solution and give you uncertainty bounds on what it thinks the solution is. So these are Bayesian pins. You can combine physics-informed loss functions with GANs, for example, for generation tasks. There are a whole bunch of other architectures like adaptive activation functions seem to improve the convergence in some settings. Different types of sinusoidal activation functions, these are sirens. You can also use LSTM architectures, et cetera, et cetera. And then there are also a whole bunch of pin software libraries that are becoming fairly well developed now. So for example, NVIDIA have this modulus library, which have a lot of a really amazing functionality for training like pins across multiple GPUs and all these different strategies that I've been talking about, and much more. So if you're interested in this as a research area, yeah, there's a lot of things you can look at. Right, so let's wrap up and just talk about these. So I already talked about the advantages. Here are the limitations. So we said computational cost is high, especially if we're just trying to train the pin each time our initial conditions train. Then the convergence properties are less well understood, like theoretically and also empirically, pins are not guaranteed to converge, and for some problems they definitely don't. And then scaling to more complex problems like higher frequencies, multi-scales, you have to change the architecture or something about how you're training the pin to improve those types of problems. Yeah, and we're working on improving these. So when it's best to use a pin, my general advice is for like forward problems, and if you're just doing simulation, a pin is generally not competitive with traditional methods. But if you're doing these type of messy problems, I call them, where you have some data, some understanding of the physics, it's kind of an inverse problem and a full problem at the same time, where you have to run these traditional methods many times, then they can be competitive, and there's a lot of interesting work in that area. So yeah, I've just this is the summary of what I've just said. So yeah, thanks for coming, and I'll see you in like 5 weeks time, 6 weeks time. So